So welcome to this new DaSCI seminar that will be focused on trustworthy learning in heterogeneous networks. First of all, I want to thank Tian for very kindly accepting our invitation. Tian is a fifth-year PhD student in the computer science department at Carnegie Mellon University, working on distributed optimization, large-scale machine learning, federated learning, and data-intensive systems. Prior to Carnegie Mellon University, she received her undergraduate degrees in computer science and economics from Peking University. She was a research intern at Google Research in 2022, received the Best Paper Award at the ICLR Workshop on Security and Safety in Machine Learning Systems 2021, was selected as one of the rising stars in machine learning by UMD 2021, rising star in data science by University of Chicago 2022, and was invited this year to participate at the EECS Rising Stars Workshop. Today, she will talk about how heterogeneity lies at the center of the constraints of federated learning, and she will present new scalable federated learning objectives and algorithms that rigorously address sources of heterogeneity. Again, thank you very much for accepting our invitation, and whenever you're ready, the floor is yours.
Yeah, thanks, Pablo, for the kind introduction. Yeah. So I'm very happy to present some of my recent works on trustworthy federated learning here. By the way, if we have any questions or comments or feedback, feel free to interrupt me anytime during the presentation. Okay. So as you may already be aware, it's becoming increasingly important to support machine learning applications without sending all user data to a central location. So enable data sharing without centralization is kind of like a pressing need for lots of applications. For example, anomaly detection in IoT devices, like across this a remote network of IoT devices. If you want to jointly train some anomaly detection models without sharing all the user data on the local devices, right? Or some other applications like adapting to pedestrian behavior on autonomous vehicles, or providing personalized healthcare on a network of wearable devices, and so on. And also in some like smart home applications or some medical or finance services where you want to jointly do some computation or either train some statistical models while not sending all the users' health data or the finance data to some central location. So this problem can be addressed under this framework, which we call federated learning. So federated learning means privacy-preserving training in heterogeneous and potentially massive networks while keeping all the user data on their local devices or in the local organizations. So such networks can be a network of devices, maybe hundreds to thousands to millions of devices, like cell phones or some other edge devices. And this network can also be a network of isolated organizations, such as hospitals or banks. And people usually call the first case cross-device settings and the second case cross-silo settings. So one kind of canonical formulation for federated learning is to optimize over this global model W to minimize such a loss function, which is a weighted average of the local losses. So capital Fk is the local loss on device K or some error functions. And Pk is some predefined weight for that device. So usually can imagine we perform centralized training and they set up where conceptually there is a central server, for example, Google, and a bunch of devices communicating intermediate information with this central server periodically to learn a good W, right? And there exists a series of challenges and properties of federated networks that make it different from prior, maybe distributed training settings in data center environments. So first, the systems can be very heterogeneous due to the variable hardware of the devices, the different network connections, and the different battery powers, and so on. And also the user data generated and residing on each device are non-identically distributed. So they're not coming from the same global distribution. Imagine that different users may have different styles of texting or have different styles of taking pictures and so on. So this issue, which we call statistical heterogeneity, can affect the entire pipeline significantly. And also communication is extremely expensive, especially in the cross-device settings, because those devices are connected with the server in wireless networks. And so communication can be a real bottleneck here. So beyond a variety of challenges in federated networks, federated learning solutions must also satisfy a number of practical constraints, right? So people care about some other like metrics beyond accuracy. So first and foremost, accuracy is important. So federated methods must converge to the correct solution efficiently under data and systems heterogeneity. And because federated learning applications, they aim to learn over massive client data using client devices as distributed computing nodes, there are critical constraints regarding trustworthiness, like robustness to device failures, to real-world data noise, like to training time attacks, for example, and fairness against sampling bias, representation disparity, like those uneven performance across different groups, data imbalance, as well as lastly privacy. And mitigating the potential negative impacts of heterogeneity in terms of these separate metrics is already very challenging. And it's even more challenging if we jointly consider all metrics which may be competing or at odds with each other. So I'll just briefly mention some of the key challenges and trends in federated learning. So for example, you have issues with communication cost, different from the classic data center settings. And because communication can be orders of magnitude slower, especially in cross-device cases. And it's also important to reduce the negative effects of heterogeneity in terms of the data and also systems. Another big issue, as mentioned before, is this trustworthiness, things like privacy, fairness, and robustness, given that the networks are heterogeneous. And also how to put federated learning in production, for example, by using some methods. There are some different practical considerations, including how to do large-scale hyperparameter tuning at scale. And today I'm going to focus on the trustworthy aspect to talk about how fairness and robustness can affect the training pipeline and how should we think about jointly satisfying robustness and fairness. And then I will talk about privacy, like to think about in the specific framework of differential privacy, which is which provides a kind of more rigorous mathematical formulation for satisfying and measuring privacy. And I'll talk about can we improve privacy utility trade-offs, leveraging some different information of the problem or the data. So first, we look at the constraints of fairness and robustness. Here, specifically by fairness, I mean fairness in terms of representation disparity. And so the goal here is to guarantee the uniform performance of all devices or all the clients across this federated network. So not to having some unfair performance across some subpopulations of the network if they are not represented equally. And here by robustness, I mean, I would consider robustness against data and model poisoning attacks. So actually, if you think more like this fairness and robustness under that specific notion of fairness and robustness, they can compete with each other. So what I mean by that is, so we look at the test accuracy of the average test accuracy of benign devices under attacks. So we see that for different levels of attacks. So here the x-axis is plotting the number of malicious devices. We see that fair methods have a worst average testing accuracy because it aims to upweight the minority groups. And because the data are not identically distributed, it may easily overfit to corrupted data. So fair methods are not robust. And also these robust methods, for example, those robust baselines based on the robust statistics. So they usually filter out the information. So the goal is to aggregate, some model updates, and then those robust methods will usually drop those updates that look differently from each other. So they will ignore noisy samples, which may filter out informative data. So here in this case, robust methods are not fair. And our insight is that statistical heterogeneity is a root cause for the tension between these constraints. And our idea is to increase model capacity, and specifically by leveraging personalization to achieve robustness and fairness jointly. So personalization learns separate but related models for each device. Instead of just fitting a single model to all devices' data in the network, it learns separate models, while also allowing for sharing some information across devices. And so personalization naturally models and adapts to heterogeneity in federated learning. And there are potentially different ways to do personalization. And in this work, we look at a simple and scalable multitask learning framework, which we call DIDO. And DIDO is inspired by the classic mean regularized multitask learning objective, but we regularize towards an optimal global model instead of the average of the models. So here we can see that each device, its local objective is HK, where HK is the local loss plus a L2 regularizer, which can strengthen the local model VK to be close to the optimal global model W star, where W star is defined as the optimal model of some aggregate function G over those local losses from F1 to Fk. So here G can be some aggregate function. For example, it can be an average of F1 to Fk. And when lambda is 0, we see that it would just reduce to training local models separately for each device. And when lambda is infinity, we are recovering learning a global model W star. So you can think of this objective as a very simple form of multitask learning. And the way we enforce the relations between two tasks is, so there is a global task and there is also a local task. The way we enforce the relations between two tasks is using this L2 regularizer in the parameter space. Yeah, so just a little bit more of the concrete setup. So robustness, I mentioned before that we consider poisoning attacks during training. So Bayesian robustness, and specifically in terms of the exact attacks, we consider label poisoning attacks or random Gaussian updates attacks and model replacement attacks. And we measure robustness by the mean test accuracy across benign devices. And for fairness, we look at the performance uniformity across the network. So the goal is, as I mentioned before, to avoid bad performance for those underrepresented devices and to encourage a more uniform model distribution. And we measure fairness by the test performance deviation across benign devices. Yeah, so to really understand why DIDO can be beneficial by itself for fairness and robustness without any additional fair or robust mechanisms, So we have this federated point estimation problem where the local objective FK is just this mean estimation problem, is to estimate the mean of n one-dimensional data points. So suppose we have a Bayesian setup. There is some random variable theta, and then the underlying models on each device are generated by adding zero mean Gaussian noise with variance tau squared to theta. So here from V1 to Vk, it's the actual model on each device. And then the observed samples on each device are generated by adding Gaussian noise on top of those underlying model distributions. So we see here, like tau is task unrelatedness parameter. So when tau is equal to 0, then the data on each device will be generated from the same distribution. And the larger tau is, the more unrelated those tasks are, or those clients are. And also we assume that they're K sub A malicious devices. So each of them having the attackability modeled by tau A, where tau A is larger than tau. So under that setup we described before, like we can explicitly characterize the closed form of an optimal lambda star, which is a function of several key parameters, like including the number of local samples, the task unrelatedness parameter, and the number of malicious and devices, and the strength of the attack. We can see some interesting trends from this closed form solution of lambda star. So recall that the smaller the lambda star is, the more we will go to local training, right? Because when lambda star is equal to infinity, it will just reduce to training a global model. So here, for example, when the number of samples on each device n increases, we will have a smaller lambda star, which means that we will go from global training to local training, because it's just that each device has more number of local samples. And it's when the task unrelatedness parameter increases, which means that when the devices or the clients are becoming more and more different from each other, it's also better to train some local models or having less collaboration. So you can also observe some other relations between different parameters through this lambda star. Yeah, and here are figures visualizing our previous results. I think we can skip this part. Another benefit of Ditto is its modularity. So, which will bring us some benefits in terms of, for example, optimization. So we can plug in any global model solver and inherit the convergence benefits of the global model solver to solve Ditto. Because we have this theorem that if W star converges with rate GT, which is some function of the number of iterations T, then there exists a bounded constant such that Ditto converges with rate C times GT. So this tells us that we can improve the convergence of the Ditto objective by we can improve the convergence of the solver that I mentioned before for the Ditto objective by improving the convergence of the global algorithm solver GT. And also, if we look at privacy, we know that Ditto preserves privacy or communication benefits of the global objective and its solver, because Ditto transmits exactly the same amount of information as any global solver, because that local objective doesn't incur any privacy or communication costs. In terms of robustness, we can plug in existing robust aggregators to robustify W star. Yeah, so here we empirically show that fair methods can be more sensitive to attacks, and robust methods can filter out those rare but informative updates from the benign and underrepresented devices. And ditto is both fair and robust on this attack. So here, MTL, which is shown in blue here, means like our ditto objective. And we also compare ditto with state-of-the-art robust baselines or fair baselines. So under different attacks described before, like for all levels of corruption, we see that ditto outperforms the strong baselines, including the medium aggregator, the gradient clipping, and CRUM. So CRUM is a method which just takes, so it first computes the similarities between different gradients or model updates with each other. And then it will only use that single gradient with the highest similarity. And also, if we look at the performance variance, ditto is also more fair than all the baselines in terms of the accuracy variance, which is shown in the y-axis here. And on average, and ditto can improve the absolute test accuracy by around like 6% over the strongest robust baselines. And in clean cases, it can reduce variance by like 10% over some fair methods. So the takeaway for this work is that first, it is critical to consider this interplays between multiple constraints in practice. And multitask learning is a principal way to learn personalized and shared models, but can also have inherent fairness and robustness benefits. And there are several interesting open questions regarding this connection between personalization and other practical metrics, for example, privacy. Yeah, so next I'll talk about privacy. Because for federated methods to demonstrate this trustworthy behavior, it's very important to protect user privacy in some rigorous way. And just note that federated learning takes a first step towards protecting user privacy or user data by hiding some of the data on their local devices without transferring them to the data centers. But still, if we look at differential privacy, federated learning doesn't guarantee differential privacy. So consider this example of a linear model where the loss is just this features x times the model parameters. And if in the federated learning update, we transfer this gradients between the server and the devices, it will basically be the data. So what people usually do is that they post-process the gradient or the model updates to limit the privacy loss. So they hide some information or add some noise to the transmitted gradients. For example, one kind of popular mechanism is to first clip the gradients to a max L2 norm of some threshold C, and then add random Gaussian noise proportional to the clipping norm C, as shown in the equation here. And here B is the mini batch, and the hyperparameters C and sigma. So here the variance of the noise is sigma squared and C squared, where sigma is some noise multiplier that is related to the privacy parameter. And so here C and sigma, they can be tuned to get a particular epsilon delta differential privacy, which is how people usually measure differential privacy. So there are two parameters, epsilon and delta. The smaller those parameters are, the stronger differential privacy guarantees they will have. And in federated settings, so recall that in the classic differential privacy literature, differential privacy is defined in terms of so the level of the unit of protection is some single sample or some single record in the entire database, right? And in federated settings, there's notion of this user level or client level differential privacy, which says that the output models will look very similar if one client changes or is removed out of training. And because the privacy budget is tight, usually people would like the algorithms to converge as fast as possible. So here, this differential privacy definition is the same as the classic differential privacy definition, except that they change the unit of protection from each sample to each user or to each client. And the goal here is to speed up convergence to save some privacy budgets. And one way of doing that is using adaptive optimization. So first of all, just to mention what those adaptive methods are doing. So there are many adaptive methods, and some of the representative ones, including things like AdaGrad or RMS-Prob or AMS-Grad or Adam. So for AdaGrad, they first precondition the gradients using some approximates of the Hessian, as shown here. And this effectively resulting in the coordinate-wise learning rates for the gradient updates, because you can see that here, if you think of the capital GT as some diagonal matrix, and then this gradient will be scaled differently on different coordinates. And the intuition here is that real and informative coordinates will have a larger learning rate, because those are the features that you might not see very often, and you want to have make more progress on those features because they're very predictive. So you apply a larger step size on that. And RMS-Prob is another way to do this preconditioning. It's using the moving average to estimate the second moment of gradients by decreasing the effect of historical gradients. So RMS-Prob and Adam usually perform better, especially in non-convex settings, while AdaGrad works well for convex problems usually. And the motivation for the work I'm going to talk about is to look at how to train DP models with adaptive optimizers. And the methods we develop will be interesting for general machine learning problems and can also be applied to the setting of federated learning. So adaptive optimizers are very useful for a variety of machine learning tasks in practice. And they're even the default methods for lots of applications, for example, for some like NLP tasks. But it has been observed that the performance may degrade significantly when they're trained with differential privacy, especially when the model dimension is large. So given the example, here on the left figure show the test accuracy versus the number of epochs of non-private training on a real-world dataset using SGD or Adam. We see that Adam has a significantly better performance than SGD, both in terms of the converging speed and in terms of the final solution it can achieve. However, in private training, vanilla DP Adam's utility will be hurt a lot than DP SGD. So it's only marginally better than DP SGD. And so the question we ask is how to effectively adapt to the geometry of gradients under differential privacy to retain the benefits of adaptive optimizers. Like one natural and straightforward way is to first privatize the gradients individually and then plug in the private gradients into whatever adaptive updating rules. So if it's Adam, we first privatize the gradients in this way, and then plug in this tilt GT, this noisy gradients, to some existing adaptive rules. And this method results in the performance I showed in the previous slide. And the issue is that the estimates of the preconditioners can be very noisy. So if we visualize the estimated second moment of gradients when the model has converged over different coordinates, we see that the estimates output by DP atom, shown in red here, is not very useful to indicate the relative scaling of each coordinate, because the variance on each coordinate is basically just a random DP noise. So it's all the same. And then this means that the preconditioner estimates are dominated basically by privacy noise. While if we look at atom, the estimated second moments of gradients is pretty informative of the relative scaling of each feature. And so here we propose to perform private adaptive optimization using some additional information to improve the performance. We consider two practical scenarios with public data or without public data. So if we have a small amount of public data that have similar distributions as training data, at each iteration, we can simply update the preconditioners using gradients evaluated on public data, because those public data can be very kind of informative of the private data distribution or some other proxy data. And so those data can usually be collected by model engineers or from some users that opt out of training during this process. And without public data, our insight is that oftentimes we have some non-sensitive aggregate statistics of the entire data set that is first easy to obtain before training because it may be just some common knowledge in the open world. And also it's pretty informative of the geometry of gradients. For example, token frequencies in natural language processing applications. So based on this information, we first obtain some good preconditioners denoted as A here. And another modification we made is to first precondition the raw gradients using A before privatizing the resulting vector, as opposed to the other way around. So the order here, the first preconditioning and then doing this privatization results in smaller noise added to gradients with a smaller magnitude. If we first privatize the noise and then do the preconditioning, the noise will be scaled in a different direction. So that's not desired. And so here the order is kind of, the modification is small, but it's important for the practical performance and also for the theoretical analysis of our algorithm. So here A is relatively, is kind of approximately the second moment of the gradients if we consider Armis prop as an example. Yeah. And we also analyze our framework theoretically in terms of convergence. At a high level, we prove that the DP noise, so the second term here, will be significantly reduced when the actual gradients are sparse. So the first term is the 1 over square root of t. So here t is the number of iterations, is the same as standard RMS prop or standard SGD. And the second term is due to the noise and is measured by this matrix norm of A, and which shows that the noise will be reduced when the gradients are sparse. So we apply adapts to both centralized training and federated learning. Centralized training, we consider sample level DP, and in federated learning, we consider client level DP. And adapts is agnostic of the definition of neighboring data sets. So in centralized training, we observe a significant improvement compared with the baseline methods of vanilla DP atom and DP SGD. And in federated learning, we apply preconditioners on the client side at each local update and compare with the private versions of popular federated learning optimizers like DP fat average and DP fat atom, again, we see that it helps with empirical performance. Okay, I see a message in the, okay. So in both settings, adapts help with the performance of the adaptive methods. Okay. So this is nice, but the assumptions of having that additional site information can still be too strong in some applications. Like ideally, we would like to rely on some additional structures in the observed noisy gradients themselves, because by the post-processing properties of DP, reusing private gradients will not cause any additional privacy loss. Our most recent work is built upon this insight that preconditioner values do not change drastically during optimization. So for example, on the real-world example on the IMDb dataset, the preconditioner distributions, they remain very similar across different epochs, which opens up opportunities to estimate the preconditioners by averaging across previous private gradients. So as a first step towards understanding the effects of delayed preconditioners, we first apply them in non-private training. So here we consider RMS prop as the specific optimizer, but we have additional results of Alagrad and Adam in the paper. So across 3 datasets, we plot training loss versus the number of epochs. And we see that, as expected, this adaptive method, RMS prop, has better performance than SGD. And for the optimizer with delayed preconditioners, to implement that, we update the preconditioner every S number of iterations. So S can be maybe 100 or 200. And then we use the stale preconditioners for some subsequent S iterations. And then we update the preconditioner again. So we see that while the preconditioners have been delayed, the training loss, it can still achieve similar training loss as RMS prop, which means that it's very robust to the staleness of the preconditioners. So the previous observation motivates the design of our final algorithm, which we call DP squared. It means delayed preconditioners for differentially private adaptive optimization. So at each iteration T, at a high level, we switch between DP SGD and private adaptive methods. And at each iteration T, we sample a mini batch B and precondition this individual gradients GIT using some vector GT. And after that, we privatize the transformed gradients by clipping and adding random Gaussian nodes. So here, the vector DT denotes either stale preconditioners when we run adaptive optimization methods, or O1's vector if we run DP-SGD. So the key here is to update GT periodically by averaging over previous noisy gradients, as shown in the equation here. So here, tilde G1 to tilde GS are S noisy gradients in the previous S iterations. For simplicity, I just index them starting from 1, but they're not actually starting from 1. So they're S noisy gradients, and if we just simply average them, we can reduce the variance of the privacy noise by a factor of S. And we have that virtual gradient, which is the average of S noisy gradients. We plug in that virtual gradient to RMS prop updating rule, get a estimate of G. So here G is a stale but less noisy preconditioner, and that can be applied to precondition our raw gradients GIT the small GIT to get some benefits of adaptivity. So here is a figure like visualizing what is exactly happening for DP squared. We first run some steps of DP-SGD, and then obtain some noisy gradients from tilde G1 to tilde GS, and then accumulate them to tilde G and update the preconditioners using tilde G. And then we run private Armis probe using this stale but less preconditioner, capital G. And then we run DP-SGD again to refresh this capital G, then run private Armis probe. So this iterative process will go on until convergence or some stopping criteria. And we also provide some like theoretical explanations for the performance of our algorithm. And in the convex case, we have which contains two terms. The first term is due to adaptive optimization, and the second term is due to privacy noise. Again, if we look at the second term, we observe that the adaptive noise can be significantly reduced compared with DP-SGD, because here we are measuring this. We are measuring this kind of noisy random Gaussian variable using this matrix norm dt, while in DP-SGD, dt is basically all-ones vector. But here, for some iterations, dt can be much smaller than 1. So here are some of the empirical results. And we look at this IMDb, stack overflow, and movie lens datasets, both in convex and non-convex cases. We see that DP squared significantly outperforms DP-SGD and DP Armis probe across all privacy budgets on all datasets. And another important parameter of our algorithm is the delay parameter S. So we'll also study the effects of that on 3 datasets. So intuitively, when we have a larger S, we will have smaller noise. However, the amount of delay will also be increased. So there's a trade-off between how much noise we are able to reduce and how much additional delay we will introduce. And the conclusion on this datasets is that there exist some specific values of delay which will achieve the greatest improvements. However, across a range of delays, all instantiations of DP squared under different S here is shown in the x-axis here. All instantiations will outperform the baselines in terms of test performance. So the takeaway is that we need to be careful when we think about DP with different optimizers or different objectives. And in adaptive optimization, we can construct better preconditioners from sighting information or from historical iterates. And there are many open problems for the exciting area of federated learning or data sharing, like related to diagnostics. For example, how to determining heterogeneity or the data similarity a priori from data before training without seeing the raw data. And how to, like in terms of fairness and privacy, how do we rigorously show fairness benefits of multitask learning? So in the previous work I talked, we only show the fairness benefits of the detail objective on a very simple linear case. And the connections to other notions of algorithmic fairness, those things like, for example, demographic disparity or individual fairness, and also other approaches of reducing DP noise, for example, with tree aggregation techniques. And also in terms of personalization, it's not clear what is an optimal personalization formulation for federated learning? Yeah, and there are a bunch of other open questions. I think that's all I have today. And all my papers and code are available on my website. You can check it out if you are interested. Yeah, thanks.
Okay, thank you very, very much for this very nice talk. So now it's time for questions from the audience. So as usual, feel free to write your name in the chat and I'll give you the turn to speak.
So Pablo, if nobody wants to, okay, maybe I can be the first person to make question.
Go ahead.
Thank you very much, Tian, for this nice presentation about federated learning. We were working in federated learning, and okay, I have maybe we are working some common lines. For instance, we are working a lot in robustness. So my first question is, I didn't see, or maybe I didn't understand, completely understand your view about fairness in federated learning. So are you considering fairness in federated learning as the same as robustness? So to defend against membership attacks, poisoning attacks, Byzantine attacks, or whatever adversary attack?
Oh, so your question is how was robustness?
Your vision about fairness, because at the beginning of the talk, okay, you were talking about fairness, okay, and robustness, isn't it?
Yeah, fairness.
So, yeah, fairness and robustness. Okay, so I don't completely understand if you consider fairness in federated learning as the same as robustness. So to make federated learning robust against poisoning attacks, membership attacks, Byzantine attacks, okay, whatever adversary attack. So what do you think? Because I didn't completely understand the first part of the presentation.
So your question is, how do we, like, is fairness as important as robustness?
Yes, or because I guess that you say, so maybe I'm wrong, okay, the fairness is the same than robustness.
Oh, it's the same as robustness. Oh, okay. So the fairness notion is kind of fairness against the representation disparity. So we want to guarantee the like the model will have a good performance on some underrepresented population. So all those population are having benign data, and so that's actually contradicts with some of the definitions of robustness. So if we think about some clients who have a very who has a very bad data, and then for robustness, our goal is to remove that data from training, and for fairness, our goal is to upweight that data or to highlight that data during training, because we want to be fair to those kind of small populations.
Okay, I see. Now I understand, because at the beginning of the talk, because you talk in the slides about the fairness and robustness, and then I didn't see, okay, your view. Okay, now I understand. Thanks. Because we are working on robustness. Okay, we have several works on how to defend federated learning against different kind of attacks. So I didn't see. Now, okay, I see. And since you are working on federated learning, I see that most of your works are on horizontal federated learning. So do you think that this presentation, can you apply in vertical federated learning or in transfer federated learning?
You mean, can the techniques be extended to other problems beyond federated learning?
No, maybe okay to work. Okay, or do you have any experience on vertical federated learning and transfer federated learning?
What do you mean by like transfer federated learning?
When
Okay.
you don't share, okay, neither the or you don't share the sample space and the feature space. Okay, you know, in the horizontal federated learning, okay, you share the feature space. Okay, in vertical federated learning, you share the sample space, but the features are different. And in transfer federated learning, okay, the problem is that you don't share, or there is a very few overlap among the sample and the feature space. Okay, I don't know if you have any experience, or do you have any work in this line of fairness and robustness and privacy in vertical and in transfer federated learning?
Also, so there's like this vertical distributed by features. Horizontal federated learning, they're distributed by samples. So you mean there's another regime where you have both?
Yes.
Oh, okay. Yeah, I think lots of the things I talked about today can be extended to those settings. For example, this multitask learning formulation. But I do think that vertical setting or the other setting you mentioned, they may have additional challenges, including like how would you like communicate things? Right. Because it's kind of like the differences between data parallelism and model parallelism. And there are a whole bunch of unique challenges with model parallelism there in those settings. And also, I guess the application cases of these different settings are different. So for the case where we distributed by features, and that will mostly happen. So based on the application cases I see, that can be mostly happen within some organizations and some different departments in one company. They have different like user features, but they cannot share user data even within a single company, but across different departments for different applications. And then that is more corresponding to this cross silo case versus the cross device case. And then the small scale cross silo case, usually they care more about privacy, and then they don't have many issues regarding like communication, or because you know those silos potentially they can be connected in a very fast networks, and then each silo, instead of just being a device, it may be another small data center that you can think of. So yeah, I think you can extend different things in from this horizontal federated learning to vertical federated learning, but they also have some unique challenges.
Okay, thank you, Tai. And regarding natural language processing, because I see that you organize the first workshop on natural language learning and natural language processing, I would like to ask you about if you now are working on real scenarios or real use cases to use federated learning in natural language problems.
Natural language problems. Yeah, I feel like I'm not specifically an NLP person, so I don't directly work on improving natural language processing algorithms, so things like training large language models, so my work usually just developing some algorithms or optimizers that can be applied to a bunch of applications, like any model or any data set or any And then I think if we specifically consider the interplays between federated learning and NLP, so first I feel like in natural language processing, the data distribution can be very different from the image data distribution. So the text data, they can always be sparse, and that will raise some interesting questions. Actually, that's very related to one of the works I talk about today, which is the privacy work. And the approach we proposed is specifically interesting to NLP applications. More interesting to that than the image applications, because in NLP applications, you have heavy-tailed data, which will make adaptive methods more effective. And also, if we think about training large language models and the interplay between federated learning, and I feel like that area is generally very open, because all the federated learning research so far have been mostly focusing on this like training model across different devices or silos. And if we consider having a pre-trained model in those federated networks and how that would affect the existing assumptions and solutions, that's totally not clear yet. Yeah.
So thank you for your vision, Tai. Thank you very much. I don't know, Pablo, if there is somebody in the room that wants to make any question for Tian. Sorry.
No, so far, no questions. Well, again, there are any questions in the room? Does anybody want to ask anything?
So in this case, Pablo, I would like to make an offer to Tian. Okay, Tian, if you wanted to make a collaboration to work together, okay, we are working on federated learning. So okay, I write you my mail on the chat. So okay, write me an email and we can make something, we can make a collaboration to think to make something. Okay. Thank you for accepting the invitation of Pablo to make a talk. Thank you very much for your questions and your time.
Yeah, thank you for the questions and the sessions, for having me here. Yeah, I'm always open to collaborations, and yeah, can be in touch. Yeah.
Well, thank you very much. So we can finish here this talk. Thank you, first of all, to Tian for all your for the presentation and the responses to Eugenio's questions, and thanks to all the attendees. So see you soon, hopefully.
Yeah.
See you.
Thanks.
Thank you.
Bye bye.
Bye bye.